Welcome to The Explainer. If you're building next-generation AI agents, you already know that reinforcement learning post-training is kind of the new frontier, but you also know it comes with some massive engineering headaches, right? Well, today, we're going to dive into how the vime streamwork, running natively on AMD's ROCm ecosystem, is stepping up to solve one of AI's most brutal hardware bottlenecks. It is a real game changer for large-scale RL workloads. But before we get to the actual solution, we have to start with this crucial question to really understand the massive memory tax that's holding back so many engineering teams. Why exactly is RL post-training causing so many out-of-memory errors and infrastructure nightmares? The answer actually lies in the sheer volume of data your hardware is forced to juggle all at once during every single step of the process. Okay, here is our roadmap for today. We'll cover 1. The RL memory bottleneck, 2. Enter vime on ROCm, 3. The AMD Instinct advantage, 4. Under the hood, 5. Performance under pressure, and 6. The feature roadmap. Let's get right into it. Section 1. The RL memory bottleneck. The core issue here is what we call the co-located squeeze. In a standard setup, your GPU is basically forced to live a double life. On one hand, it has to hold these massive Megatron training weights just to actually update the model's parameters. But on the other hand, it has to simultaneously maintain the vLLM inference KV cache to generate the rollout tokens. They are fighting a brutal zero-sum game for the exact same pool of device memory. For engineering teams, this usually means relying on aggressive tensor parallelism, crazy complex cluster topologies, and severely limiting model sizes just to keep the whole shebang from crashing. It is a massive constraint on innovation. Moving on to Section 2, enter vime on ROCm ROCm. To fix this, vime adopts a brilliant three-stage decoupled design. You can think of vime's architecture a lot like a high-performance car. Step 1 is the training side, powered by Megatron-LM. This is the engine doing the heavy lifting of parameter updates. Step 2 is the rollout side, driven by vLLM and a router. These are your wheels hitting the road, executing the inference sampling to produce training samples with those all-important reward signals. And Step 3 is the data buffer. Think of this as the high-speed transmission connecting the two, managing prompt injection and custom rollout logic. By explicitly decoupling these stages, vime brings much-needed organization to the absolute chaos of RL training. Which brings us to Section 3, the AMD Instinct advantage. Just look at the sheer scale of this number, 288 gigabytes. That is the massive HBM3E memory capacity available on a single AMD Instinct MI355X GPU. When we talk about solving that co-located squeeze we just went over, this is quite literally the silver bullet. With this kind of unified headroom, you can comfortably fit large models for training without having to shard them across complex, heavily distributed network topologies just to survive the memory pressure. It drastically simplifies your entire cluster utilization. And when we compare the widely used MI300X to the newer MI355X, we see an incredible leap. The capacity jumps from 192 gigs of HBM3 to 288 gigs of HBM3E. But pay really close attention to the bandwidth. We go from 5 terabytes per second to a staggering 8 terabytes per second. So why does this actually matter for you? Well, because RL rollout, specifically autoaggressive token generation at scale, is fundamentally bound by memory bandwidth. Every single decode step has to load the full KV cache and model weights from HBM. Bumping that bandwidth up to 8 terabytes per second significantly shortens step latency and just massively improves throughput during the rollout phase. And that phase, by the way, dominates your overall training time. All right, Section 4, under the hood. Now that we know the hardware specs, let's look at the system-level mechanics to see how this runs flawlessly out of the box on AMD GPUs. First, the framework uses a ROCm-compatible fork of Megatron-LM with patch training loops. But the real magic here, that's the co-located IPC weight synchronization. After each optimizer step, Megatron syncs the updated weights directly to the vLLM engine via IPC routing using stable device UUIDs. This means your rollout workers always generate from the absolute latest policy without a single costly network round trip. Finally, to keep everything organized, it relies on strict GPU visibility management via HIP_visible devices. This ensures that Ray actors and Megatron workers aren't blindly fighting over the exact same GPU resources. Let's look at the actual data in Section 5, Performance Under Pressure. The hard performance data proves this works exceptionally well on the Qwen 3-8B model running on the MI355X. First up, we see a sustained throughput of around 4,100 tokens per second per GPU across 100 training steps. Second, check out the log prob divergence. It holds remarkably steady at about 0.012. Now, this is absolutely crucial. It proves the IPC weight synchronization is working perfectly, completely preventing the log prob drift that would normally corrupt your policy gradient signal. And finally, the raw reward successfully climbs from 0 up to around 0.6 by step 100 on the DAPO math dataset. This proves a clear, powerful optimization signal. The freshly initialized policy is successfully learning and favoring the exact reasoning patterns that are rewarded by the verifier. Finally, Section 6, the feature roadmap. As we all know, the open source ecosystem never stops moving, and the roadmap here includes some massive upcoming features. The teams are working on full vLLM router and prompt disaggregation support to further untangle these workloads. There's also FP8 pipeline optimization on the horizon to squeeze even more throughput out of the hardware. They're bringing R3, which stands for Rollout Routing Replay, specifically tuned for AMD Mixture of Experts workloads. And perhaps most excitingly, they are building out Agentic RL for complex multi-agent settings and multi-turn tool calling. I'm going to leave you with this provocative thought as we wrap up this explainer. For years, reinforcement learning post-training has been completely bottlenecked by rigid hardware constraints and brutal memory limitations. But now, with frameworks like vime decoupling the software and AMD's Instinct GPUs providing a massive 288 gigabytes of open, high-bandwidth memory pools, those old constraints are basically gone. So the real question is, with these hardware limits removed, what boundaries are you going to push next in your AI agent development? Thanks so much for joining me today as we broke down this incredible source material. Keep experimenting, keep building, and I'll see you in the next explainer.